go ahead and get started. Thanks for coming, everybody, although I know you have to do. Today, I'm delighted to introduce Fernando Diaz, who, as you probably know, is one of our new associate professors. I've known Fernando actually since he was a graduate student. We went to the same place, although many years apart. And Fernando he completed his PhD about 15 years ago. So this is what you might look like in 15 years if you work hard and have some success. And although I've known Fernando for a long time, he's done so much that I actually made myself some notes so that I would do more than just say, he's amazing and he's done everything, although that's true. He's worked a lot until he got here. I guess now he's retiring to academia. But up to now, his career has primarily been in industry, in research labs. And he's worked at amazing places. He was at Yahoo Research for 5 years, back when Yahoo was a powerhouse and had really amazing research labs. And in fact, he was on the PhD committee and really kind of co-advisor for one of my PhD students here at the LTI during that time. He was at MSR for 5 years. He was at Spotify as the director of research. I'll bet you didn't know Spotify had a director of research, but they did, so you might want to talk to him about that. He was at MSR as a research manager and assistant research director for a couple of years, again at MSR going back, and then he's been at Google most recently. So he's really got rich experience and is a wonderful resource for you guys to draw upon. You've got lots of sort of professional academics, but Fernando brings something that the rest of us don't really have. His research, he's done everything in search over the years, but he's especially worked on the design and evaluation of search engines, and so he'll talk about that. That kind of covers a wide range of stuff. And in recent years, he's been working on fairness, accountability, and transparency in algorithms, which of course is really hot these days, and so a good thing to talk to him about. One last thing I want to mention, often when people go to industry, even in research labs, they kind of disappear from the academic world. We see them at conferences, but they're kind of not as big a force in the community. And Fernando's really always been the opposite of that. So those of you who are involved with search, we have Trek every year. It's now 30 years research forum that the research community uses to develop new leading edge problems and data sets for people to do research on. And Fernando has been more involved in that than I think anybody else I know. He worked on the web track for 2 years, temporal summarization and real-time summarization for 4 years, fair ranking, and most recently the tip of the tongue retrieval track. And so even from industry, he has been really helping to shape what has been important for the research community and especially the academic research community, which is really, really unusual. So I'm excited that we've got Fernando here at CMU, and also I'm excited he's going to talk today. So I'll turn it over to him.
Thanks, Jamie. And thank you, everyone, for joining me. Jamie did mention that it's a community, right? So it's a research community. So even though I've participated in that community, it wouldn't have succeeded without everybody else collaborating with me. And today, I'm going to do, instead of a flyover of my research, I'm going to go a little bit deep on some research I've been doing over the past couple of years in collaboration with Andres Ferrero and Bhaskar Mitra. But before I get started on that, let me just describe a little bit about my research and where it's at right now. So as Jamie mentioned, a big part of my research right now is on information retrieval. So specifically within that domain, I'm working on retrieval enhanced machine learning. So how do I augment a machine learning system with access to, say, a search engine in order to improve its performance? And there's a plethora of recent results to demonstrate the efficacy of this approach, and we're currently exploring a lot of different extensions, primarily from the IR perspective of how to advance these systems. Jamie also mentioned the tip of the tongue retrieval research that I've been doing recently. This is really trying to help people who are trying to re-find information that they've experienced in their past. Say, you saw a movie when you were a teenager, you don't remember the name. How do I actually design a search system to be able to support you in re-finding those memories? And then finally, evaluation, which I'll be talking about today, is kind of a core area of my research broadly in IR. The other big chunk of my research has to do with the broader impacts of AI. So this deals with fairness, accountability, transparency, and ethics that I've been thinking about for the past 6 or 7 years. And most recently, I've been looking at the interaction between AI and culture. Okay, so culture here, what I've been looking at specifically are things like the culture industry. So music, film, literature, how is that impacted by AI, either in the generative sense, so as these generative technologies begin to influence the types of content that's created, but also in the distribution sense. So recommender systems, search systems are really affecting how content by different creators is actually distributed, and can we better understand how that comes into tension with the types of principles we've come up with respect to cultural distribution in the past. So of course there's an intersection here between information retrieval and the broader impacts of AI. I've worked on fair ranking evaluation, so how do I assess whether or not a specific ranked list of items is fair to different stakeholders. And then secondly, in the context of AI and culture, I've been looking into operationalizing public service media principles, so principles of content distribution in the context of recommendation and search. Okay, so today's talk is going to sit right about here. So it's going to be a pretty IR influenced talk, so it's going to be a lot about IR evaluation, but a lot of it is going to be inspired by the broader impacts, and I'll be bringing in a little bit of fairness work here. All right, so let's dig in. First, I want to introduce this concept of metric-based evaluation when we're evaluating any sort of machine learning system. So here I have on the left-hand side my classic machine learning output. So X I'm defining as the instance that I'm trying to make some prediction of. F is my statistical or machine learning model that, given X, will make a prediction of some output, scalar, categorical, or some structured output. And when I'm evaluating a system using human raters, I will pass this output to the human rater, and they will give me some quality score. Here I'm defining it as mu of the input and the output. Okay, so the rater is going to see what was input of the system and what the system output, and then give it perhaps some score on some scale, and feed it back to the model developer to assess whether or not the system's actually good. So metric-based evaluation from the automatic sense tries to do this without the human rater, right? So the machine's going to, again, provide my input instance and the model prediction, and then I'm going to also feed this algorithm or this formula some side information. So I'm going to call that side information evaluation data. Now, historically, when we think about machine learning evaluation, that might be the true label of X, but I'm gonna relax that a little bit and say sort of it's just any information that helps me decide whether or not f of X is the right decision. So now my automatic rater is going to output mu, or that is really intended to approximate the human rater. Okay, so when we talk about evaluation data, there's various styles of evaluation data we can look at. There's a gold standard approach that you see in a lot of NLP systems with a target string. So perplexity, blue, and rouge are in this family of evaluation data. We can have instance ratings, so I might have an X, Y pair and some rating on some scale. You find this a lot in industry where you have censored feedback from people like CTR. And then finally, and this is what we will be talking about today, is partial ratings, right? So the output of the system in this case is not given a rating, but some aspect of it. So the aspect of the prediction here, yi, is given some partial rating. So you can think about a y, for example, being some a research ranking, and yi being the relevance of an individual item in that ranking. But we can think about other ways of decomposing a rating or decomposing a prediction and providing a rating for that individual component, which we can then incorporate into our evaluation metric. All right, so at the end of the day, we do have these metrics, but we care about preferences between systems. So we can think about two types of preferences here. The first type of preference, which I'll call instance level comparison, is saying that, let's say I have two systems A and B, some fixed instance X, and I want to decide based on the system predictions which one's better. And then population level comparison, I'm going to say, given two systems A and B and some sample of instances X, which system is better? Now, if I do metric-based evaluation, what I'm doing here is, in the case of instance level comparison, computing the metric mu for each of the predictions independently, and then saying that I have a preference between A and B based on the difference in the metric values. Population level is sort of the same thing, except what I'm going to do here is just essentially I can compute some aggregate of the metric values across the sample and then say that A is better than B if its aggregated metric values are bigger than the aggregated metric values of B. Okay, pretty straightforward, and sort of we evaluate machine learning systems this way all the time. Now, an alternative way to evaluate a system is to, in a human rater context, instead of saying I want to get a rating on an individual system prediction, to say I have some input X and two system predictions from A and B, and I'm going to ask the human rater to just give me a preference between those two things. Okay, so preference here is represented as delta. And for those of us who've done, say, crowdsourcing experiments, we've seen things like this, where this is a search context. I have a query at the top, which we can think about as our X. And then on the left-hand side and the right-hand side, I have two different rankings for that query. The user or the assessor here is asked which one is better, which ranking is better, and then that is my my instance level preference for that for those two systems. This is, you can do this for a wide variety of tasks. So here is text to image generation. Again, I can give it some X and two images, and I can ask the assessor which one's better and perhaps which one's better along different dimensions. Those of you that are familiar with RLHF and the recent ways that we've been training the natural language generation may recognize as instance level preferences as one way to actually train up one of these systems. At the end of the day, all these things do ground out in some human actually making a judgment about the preference between these two system predictions. Okay, so what are we going to be talking about today? So far what I've talked about is in terms of human evaluation, doing metric-based human evaluation, so asking for point-wise metric values for individual system predictions. Also, preference-based human evaluation, so giving the side-by-side comparison to a person and asking them which one's better. We've looked at metric-based automatic evaluation, and the missing sort of square in this table is automatic preference evaluation, which to the best of my knowledge hasn't really been studied in the community, and I'm hoping that we can explore in this talk. Okay, so let's get started with our specific domain today, which is ranking. So ranking problems I'm going to define this way. So given some context and some collection of items, return some ranking of items that satisfy the user's information need. So this is a quite general statement, and it covers a wide variety of different tasks. So I have keyword search, where the collection of items is documents, and I want to retrieve relevant items at the top. I might have question answering, where I'm providing a list of answers, and I want the correct answer close to the top. Recommendation, which is a third line here. I have some user item interaction history, some catalog of items. I want to present novel items to the individual. And then finally, we have autocomplete, where you might have some prefix string as you're typing a document. I have a ranked list of suffixes to that prefix, and ideally I want to present some suffix that's correct or desirable by the user. All right, so these ranking problems occur all over the place. So web search is a canonical example, but if we think about recommendation tasks, those are happening in a wide variety of online platforms. Autocomplete is one that's not covered here, but it is one that's getting a ton of use at the moment. Okay, so what's going to be out of scope today in the rest of this talk? So I won't really be talking about graded relevance. So what that means is I'm only going to be talking about whether or not an item in this ranking is relevant or not. It is covered in the paper, but I don't want to get into the technical details there. I'm not going to be talking about something called multi-turn retrieval. So I'm not going to be talking about users interacting more than once with a ranked list, even though that does happen. I won't be talking about delayed rewards, so evaluating a system according to, say, subscriptions downstream or even session satisfaction. I won't be talking about evaluation beyond relevance, so you can think about diversity or fairness. That won't exactly make it in, although some flavor of it will. And then finally, I won't be talking about non-list layouts, so grids, etc. I will be talking about a lot of interesting things, but I really just want to sort of be explicit about what's out of scope today. All right. So yeah, you can ask a question.
I wonder, are you going to, I think it's very nice you lay out what you can talk about or what you're not talking about, but are you going to talk about your instance or collection? How do you sample those instances and collections? But right now, you're just distinguishing that into two settings. But I think in my reaction when I read your idea, I think the most very crucial issue is how do you sample those instances, or how do you sample all the data collections when you apply your methodology, because that's crucially impact what's your observation. So are you going to talk about that?
So when you say sampling for evaluation, you mean?
Yeah.
I'm going to assume that, I'm going to essentially assume the same, I'm going to make the same assumption that most evaluation research makes, which is that I'm given some gold set of labels already. So the sampling has been taken care of by somebody else. I agree with you that, that's going to be crucial.
But someone else is a huge issue.
Yes, of course.
I think I'm very experienced in evaluation for decades, but I find that there's a shift of the data collection. How do you generate the data collection for evaluation? That's actually a huge deal.
I agree. And so I've tried to decouple the sampling from how I'm actually computing the preference in this case. One of the things that I think would be an interesting line of future research would be how do I efficiently sample so that I can better evaluate systems, right? Which right now you can think about, it's happening either heuristically or randomly, right? Neither of which is desired. In this talk, this is all, I guess that's the sixth thing.
In your course, you're designing on this, right?
Yeah.
That part I'll be very interested.
Okay, great. Guest lecture. Okay, so what's the information retrieval problem? So imagine I have some user that is approaching the system with what I'm going to call an information need. Okay, so it's something in their head. It's not exactly the query. It's something that happens before you've actually issued the query. But once you have this desire to find the information, you will express it as some query. So this is step 2 here. And then the system, the IR system, is going to provide some ranking of items from the corpus. Now, I want to be quite explicit here about what this looks like from an evaluation perspective. So first is that the system only observes the query. They don't see the information need. Right? And what that means is that multiple information needs can result in exactly the same query or a similar query. So there's some ambiguity about what the state of the user is when they're issuing the query, because multiple users could issue the same query. Now, recommendation can be seen as a similar problem. So user approaches a recommender system. So you go on a specific part of Spotify or Netflix, and you're looking for new media. You again have an information need, but here you're not going to be explicitly representing your information need. Rather, the system is going to say your request is based on your viewing or your listening history here. Nonetheless, based on this history, the system is going to be generating some ranking of items from some catalog. But just as we had with information retrieval, the system only observes the history, which means that there's going to be some ambiguity about the user's information need, especially if those different histories collide in some way. So if two individual users approach a system and they have a very similar listening or viewing histories, but very different information needs, the system is not going to be able to disambiguate those two things.
So what does history mean? F0354?
This is a history of, say, songs or movies that you've seen in the past.
Those are IDs?
Yeah, those are IDs, yeah. Mm-hmm. Okay, so the ranking evaluation problem is given some observed requests, so the query or the history, and two rankings, pi and pi prime, determine if there's a preference between pi and pi prime. Okay. So one way to do this is to gather point-wise item labels. So what does this mean? It means that for each item in this ranking, I've asked either users or raters to provide some quality grade for that with respect to the information need. Now the system, in hindsight, might observe ratings for an individual information need. So for example, if you're in a search system or a recommender system in production, you don't see the user's information need, but you do see what they clicked on and what they actually interacted with. So they get the feedback for the individual information need. Or if I have some expert annotation, say in a mechanical Turk experiment, what I might ask the assessor there is to say, you know what, over all the possible information needs that you could imagine generating this query, what would the rating be of this item? Now, importantly here also, and I think Yiming was mentioning this as well, is that ratings are usually or almost always incomplete. So these corpora of items that you're actually ranking are huge. And so for any one information need, it's going to be impossible to go through the entire corpus and ask for a real rating for every item. Okay, so metric-based evaluation uses these point-wise item labels in order to compute an evaluation metric, as we were describing earlier. So this will be something like a utility or quality score, and you can sort of, the score is on the entire ranking pi, okay? So we're going to say, as we said before, that we prefer pi to pi prime if the metric value for pi is greater than the metric value for pi prime. Okay, so pi here, or sorry, mu here is evaluation metric, so it might be something like average precision, reciprocal rank, NDCG, if you've heard of that metric, all sorts of different ranking evaluation metrics that are based on the item labels. As one example, this is a metric that's quite recent, but has been used a lot, called rank bias precision. Essentially what we're doing here is we're iterating over the rank positions of all the relevant items in the ranking, okay? And we're going to model the user's impatience with respect to where those positions are. So I'm aggregating the quality of the individual items discounted by the rank position. So the discount factor here is this gamma, and it's raised to the power of or some function of the power of the rank position of that relevant item. So if I have all the relevant items at the top, I'm going to have a good metric value. As I go farther and farther down the rank list, the gamma values are going to get much lower, and so the metric value is going to be going down. So gamma here is a hyperparameter of the metric. As the value is bigger, the user will be more and more patient. And so as you move the items down the rank list, the user is going to be more tolerant of it being lower. As gamma goes towards 0, the user is going to be impatient. So you're going to want, the users are going to want that item in the top 1 or 2 positions. All right, so remember, I'm interested in the difference in these metric values. And so one of the things I can do with RBP specifically is to explicitly represent this difference in metric values as a summation of the difference in these gammas. Okay, so this is the equation on the left-hand side of this slide. On the right-hand side, what I have is for all possible positions of the relevant item I, what is that difference, right? So I'm disaggregating that summation, and this is basically one sum end in that summation. And the reason I'm presenting this this graph is to demonstrate that, you know, for most of the rank positions in this ranking, you're getting relatively no contribution to the summation, right? So it's pretty flat here. So unless one item is relatively high ranked and the other item is relatively low ranked, there's going to be no contribution to the metric difference here. And the implication is that you have what I'm calling low robustness to user behavior. So if you have somebody with very high recall requirements, so if they're looking for tens of relevant items, say in an e-discovery or literature review, the metric difference is going to be quite small. Okay, so the metric is going to be is not going to be able to distinguish those two systems very well. And secondly, if I have a lot of relevant items judged, then I'm not really using those items because those items are lower down in the ranking and therefore are contributing less to the metric value. And so these top-heavy metrics that we use in retrieval evaluation all the time are mainly only capturing these dominant user behaviors, so the stuff at the top, but really not paying attention to the users who have deeper information needs or using the data really efficiently. So this is a plot of a reciprocal rank and the probability of a tie in reciprocal rank dependent on the position of the first relevant item. So imagine I have two rankings, pi and pi prime. One of the rankings has the relevant item in the position 1, so that would be 1 in the horizontal axis. What's the probability of tie in pi prime? It's going to be relatively high, and so more than 50% of the other rankings are going to have a tie across a variety of data sets. So this isn't great if I want a metric to be able to distinguish a pair of systems. And so this is what's called a ceiling effect. If I have the metric values that are sort of bouncing around the top and being saturated, I can also have floor effects if I do metric-based evaluation, where the bottom of the metric value is actually saturated and you really can't distinguish systems because they're all equally poor according to the metric. Okay, so let's go back to the ranking evaluation problem, right? Given an observed request, blah, 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 I have two rankings, and I want to determine whether or not there's a preference. Can I directly actually measure the preference between pi and pi prime without having to go through these metric computations first, in the hopes that I'm going to be able to better distinguish systems? So we know from human rating experiments that side-by-side evaluation is a thing that we can do, right? So here, again, is a different interface for doing the side-by-side comparison. And the results in the community demonstrate that side-by-side comparisons are really good for being able to understand exactly what's going on in the preferences between systems. So here in this result, the preference between systems is decomposed into different aspects of the ranked list: relevance, authority, diversity, freshness. And so side-by-side comparison from a human perspective in search ranking is actually something that's quite powerful and is used all the time, including in industry. So the problems here are that side-by-side comparisons are biased in some way, right? So depending on the guidelines that you presented to the assessors, if the assessor's individual need is being reflected, it means I'm biased according to the assessors that I've selected, right? So the assessor's judgment on the preference between the two rankings will be based only on their personal preferences, not on the wider population of possible users. And secondly, if I've told the assessor that they should be doing the assessment according to their model of what people are interested in, it's biased by the user's model of what the population of information needs is. Now, in addition, there's a standard cost to human evaluation, which means it's costly to run the user study. You need to train them, you need to pay them. Moreover, labels are not gathered in a naturalistic environment, right? So the users are not actually involved in a search task. They're being asked to rate two items. And so there might be some divergence between the assessor's prediction about what's better and what is actually better to users in reality. So one question we might ask is, can we actually, since we have all these production systems lying around, can we get a preference between rankings in a production setting? The answer is yes. There's a really nice work by Thorsten Jacquims from a long time ago, 20 years ago now, I guess, where he demonstrated that you can do essentially side-by-side comparison in a way that is obscure so the user doesn't know that they're participating in a side-by-side experiment. So imagine I have some requests and two rankings, and I want to figure out whether or not the user prefers A or B. I don't want to present the rankings side by side to the user because that's going to influence their user interface. It's no longer going to be the same sort of interface that I've designed the system to really optimize for. So can I actually gather this preference information without changing the user experience? Yeah, so here we go. So here's our user who approaches the system with the information need, and I have these two rankings, A and B. The interleaving algorithm does the following. So first what I'm going to do is initialize the target ranking that's going to be presented to the user as empty. I'm going to flip a coin in step 2, pick A or B, pop the top item from the selected list, and put it at the bottom of the interleaved list, pick the top item from the other list and add it to the bottom, and continue on until you get to the bottom of the ranking, and then present that interleaved ranking to the user. So here's the interleaved ranking that's presented to the user. What I can do is, based on the clicks that I'm observing in this interleaved ranking, decide which of the rankings is actually preferred by the user. Okay, so this is really clever. It allows me to actually get that preference information without disturbing the user experience. So interleaving has been correlated with a lot of offline and online metric-based preferences. It's much more granular than metric-based preferences, so it's more sensitive and can detect differences between systems, and as a result, require much less data in order to run an A/B test. So interleaving, nonetheless, still is biased in the sense that you're capturing the specific users who are engaged in this test's preferences, right? So you're only getting feedback per information need for a preference between a ranked list. Now, you might have repeated impressions across a population of users, but that aggregation is still going to be dominated by the dominant behaviors in those populations. So if some dominant groups are interested in, say, intent A versus intent B, then that's going to be manifest in your preferences. Whereas you may want a system to be robust and satisfy both intents A and B. Moreover, interleaving, again, like most online experiments, has sparse labels, and moreover, new rankers have to be rolled into an entirely new interleaving experiment. So it scales and squared. Yes?
So your coin, you're tossing a coin to choose from list A or list B. The coin has to be a fair coin?
Yes.
Then how you possibly reflect the user's preference? So I think if the user has some preference, the coin cannot be a fair coin. A fair coin means 50-50% from one list or another. So that means the user does not really have a preference. So maybe I misunderstood.
But you're running this experiment over and over again.
I still.
Right. So there's going to be there's going to be, users are scanning from top to bottom, and they're exiting with some probability, let's say, right? And so the reason you're flipping the coin is so that the top position, say, has equal probability from both of the two rankers.
Yeah.
Right? And so the user doesn't know which ranker it's coming from. And so you're essentially saying sort of like, I'm going to present you with the random item at the top. Which one are you going to click on it?
Oh, okay.
Okay. All right. Any other questions? Yes. Yes, you can. So I presented really the vanilla version of interleaving. There's been multiple extensions that are quite nice. Yeah. Yes.
How do you attribute for credit in cases where you have the same results coming out of those rankings?
Yeah, there's a few sort of like technicalities in the algorithm that deals with duplicates. Yeah.
But if you don't toss in coin, you just round the robin, you take the first one from A, next one from B, and just interchange that. Would that be the same?
No, you have to. You do have to flip the coin because you need the say the top position, for example. You need some probability of exposure from.
Do that again, then, okay.
Yeah.
I guess. Okay.
Okay. All right. So let's return to some desiderata that we might have about evaluation in general, and specifically offline evaluation. So one desirable property of an evaluation scheme is that it's offline, so I can actually assess a system or a pair of rankings without actually going to production. Second is that it's reusable, so I don't have to rejudge an entire set of new documents every time I get a new ranker. Third is that I'm explicitly modeling the preference between a pair of rankings, right? So this is not done in metric-based evaluation. And then finally, I want it to be as unbiased as possible across users' information needs and browsing behaviors. And so if we reflect on the types of evaluation that we've reviewed so far, so metric-based evaluation is definitely offline, it's reusable, so I can have multiple systems come in and I can compute a score for them. It's not computing an explicit preference, and it's not unbiased over user information, user needs, precisely because of that graph I showed earlier, that the users with higher recall requirements are not captured here. Side-by-side comparisons offline, again, are offline. They're not reusable because each time I have a new system, I have to have a whole new set of side-by-side experiments. You are gathering an explicit preference, but again, depending on how you're training your assessors, it's not going to be unbiased. And finally, interleaving, well, it's definitely not offline. It's not reusable because you need to run an entirely new interleaving experiment with each new system. You are gathering an explicit preference, but you are still biased by the information needs. So, well, what I'll be talking about for the rest of today is something I'm calling preference-based evaluation that satisfies all these properties. And so the way we're going to do this is for the offline and reusability properties, I'm going to keep using point-wise item labeled items as traditional metrics have been using. I'm going to define a new preference function that allows me to explicitly model preferences. And then finally, I'm going to I'm going to have an unbiased preference over user information needs by doing a uniform weighting over the possible needs. And we'll see what that means in a little bit. All right, so let's do a little bit of warm up as far as what we're going to be doing today. So imagine I have a user who's interested in exactly one relevant item. So they don't want two, they want three, they want exactly one. You can imagine sort of navigating to some home page being a task like this. And so we can ask ourselves, between these three pairs of rankings, which of the rankings will be preferred? Remember, the user's looking for exactly one relevant item. Let's go from left to right. A or B?
B, right?
Yeah, B. How about this one? Right here? Yeah, I think I heard B. And then the last one? Remember, I'm looking for exactly one.
Equal to equal.
That's right, they're equal. All right, now let's try it again for exactly two. From left to right.
The equal is the first one.
Second one. A.
A is better. A is better.
That's right. Very good. And so this is, I wanted to keep this in the back of our head as we go through the rest of the slides, because this is essentially the principle behind the following evaluation scheme. So it's something I'm calling the search efficiency principle. So a searcher interested in exactly k items is going to prefer a ranking where the kth relevant item is ranked higher. Now, this might sound obvious, right? But I want to be really explicit here because it's not a really strong assumption, and I think it's the only assumption I need in order to do the rest of the evaluation scheme I'll be talking about today. Now, keeping in mind all the things that are out of scope, I can't think of very many cases where this principle won't be satisfied. Okay. So we're going to build off this by turning to some work from, I guess 15 years ago now, by Stephen Robertson, who's quite influential in the information retrieval field, where he started to think about metrics as really being aggregations over what I'm calling pseudo-populations of individuals based on recall level. So remember that each request reflects some possible number of information needs. So users might be interested in one relevant item, two relevant items, all the way up to, say, m relevant items. And traditionally, when we think about pseudo-populations within the information retrieval community, we might think about subtopics, right? But here what I want us to talk about, or what I want us to think about, is the recall levels. So I might have some people interested in one relevant item, another population interested in 2 relevant items, and so forth. And what we can do is we can derive these different subpopulations based on the item labels. So what does this look like? So I have information need, and I have some labeled items. I have rankings A and B. Zeros are not relevant, ones are relevant. And essentially what I have here is a pairing of the recall levels. So recall level 1, ranking A has it at position 2, ranking B has it at position 1, recall level 2, ranking A has it at position 3, and ranking B has it at position 5, and so forth down the list. And what we're going to be asking ourselves is, for users interested in exactly one relevant item, i.e. recall level 1, which of these 2 different rankings do I prefer? Okay, and I can go for these 3 relevant items. I can go from user wanting 1 relevant item all the way up to 3 relevant items and aggregate these different preferences I have between the recall levels. And I'm going to call this recall pair preference. So again, the input to this, this evaluation measure is a pair of rankings, and what I want to compute is the expectation that the user with recall level I prefers pi to pi prime. So the way I'm going to do this is just to look at the difference in the rank position of the ith ranked relevant item and aggregate over all of the different recall levels. Okay, so I have some probability distribution over recall levels. For right now, what I'm going to assume is that this is uniform. So I want to be as robust as possible across all the different recall levels. Now, of course, we can think about other non-uniform ways of weighting this. So if I believe that, say, more people have a recall level of 1, then I might use the inverse of the recall level or some DCG style weighting for the recall level, as I have here. All right, so empirically, what does this thing look like? So empirically, it's quite correlated with the metrics you would expect it to be correlated with. So on the upper left-hand side here, the inverse RPP is quite well correlated with reciprocal rank versus DCG RPP being correlated with, with NDCG, and regular RPP being correlated with average precision. So this is good because it gives me some sort of convergent validity to the metric itself. And if I look over on the right-hand table, what I'm computing here is for each row, which is a different data set, the ability for it to statistically distinguish pairs of systems that are evaluated on that data set. Okay? So this is something developed by a metric developed by Tetsuya Sakai called discriminative power, and it measures essentially the percentage of comparisons with statistically significant difference in measures. And so what we observe here is that if we compare RPP and its variance to baseline metric-based evaluation, we're getting much more detected differences between systems, which means it's quite good at differentiating between systems that are different. Okay, so this is the average case, an average over all recall levels. So if I don't know what a recall level is, then what's the expected performance? But what we can do is we can also say we can look at specific subpopulations within these different recall levels. So for precision orientation, what I can say is that I can look at the searchers who are satisfied by at most or exactly 1 relevant item. And for recall orientation, I can look at searchers that are satisfied only when they find every single relevant item. All right, so let's think about that first population, which is the precision-oriented searchers. So these are those interested in exactly 1 relevant item. I'm going to call this best case preference because these are the sets of users who have to put in the least amount of effort in order to satisfy their recall requirements. And in order to compute my best case preference, what I'm going to do is just look at the position of the top ranked relevant item. And I'm going to say that I'm preferring pi to pi prime if the top ranked relevant item in pi is higher than the top ranked relevant item of pi prime. Now, those of you familiar with reciprocal rank will notice that this is kind of exactly what reciprocal rank is doing, which is good because you have this flavor of a high precisionness in the best case preference. Now, there's a problem. Remember that earlier on I presented this graph that showed that reciprocal rank is observing a lot of ties, right? If you have a lot of systems that have approximately the same amount of the same position of the top ranked relevant item, then you're not going to be able to distinguish them. And this is actually something that is getting to be a bigger and bigger problem as retrieval systems are getting stronger and stronger. So one of the things that we can do in order to break these ties is appeal to some work in social choice theory called lexicographic sorting or lexicographic evaluation. Okay, so what I'm going to do is, instead of just looking at the top ranked item, if there's a tie, I'm going to back off to the next highest ranked item, and while there's a tie, keep going down the rank list until I find a difference in rank position, and then claim that one of the rankings is better than the other based on that. Now, this is actually quite nice because it provides me with a total ordering over all possible rankings that a system can provide me with for a given query. So what does this look like? So again, imagine I have rankings A and B where red is the relevant item. So first relevant item, equal position in both. So reciprocal rank here would say these two rankings are tied. Instead, what I'm going to do is I'm going to back off to the second ranked relevant item. Again, there's a tie here. But once I get to the third, I'm going to say that ranking B is better than ranking A because the third ranked relevant item is higher in B than in A. Again, so here we have a similar table on the left-hand side that's showing the discriminative power of lexi precision under a couple of different weighting schemes. So weighting scheme RRLP is essentially weighting the difference according to the reciprocal, and sign LP is doing it according just to the vanilla sign of the difference. And in all cases, it has more statistical sensitivity than reciprocal rank does on all the data sets we evaluated on. Now, the graphs on the right-hand side here are demonstrating the number of ties you're going to observe between a pair of systems as I'm removing labeled data from the evaluation. And so in green here, I have reciprocal rank, and as I begin to remove labels from the system, I'm going to observe, as I add more labels to the system, I'm observing more and more ties because there's going to be more and more indistinguishability at the top of the ranking here. And so this is why the green line is going up. What I'm finding with lexi precision is that I'm adding more labels, I'm actually able to distinguish systems even more, which is a behavior that we want in a metric. So we talked about best case, now let's talk about worst case. So there's a couple of different ways to think about worst case here. So the first way to think about it is in terms of recall levels, the same way we did with lexi precision, right? So I can say the worst case is the lowest recall level, so the user who's looking for all relevant items. Alternatively, what we can think about is all possible relevant states, right? So imagine searchers approach a system with different amounts of background knowledge. So if I'm searching for, if I'm doing a literature review on attention mechanisms, right? There's certain papers that I already know about. And so probably those, even though they're topically relevant, aren't really going to be desirable to me. And so I would consider them maybe not so relevant in a personalized context. Now, given that I don't know anything about the user's previous experience, what I can do is I can have a conservative model of the possible user background information. So here in the figure at the bottom, what I have is on the left-hand side is kind of the standard way we think about relevance in evaluating ranked lists, which is, I'm going to say, is a union of all possible user relevance states. Instead, what I want us to think about is really decomposing that into all possible user relevance states, which is like what's the different combinations of items that the user has seen in the past. And so it's going to be essentially, if I have m relevant items, I have to the m-1 different relevant states that I have to reason about. Now, the convenient thing here is that if I want to think about the worst case, all I need to, the worst case in both the possible relevant states and the recall level is going to be exactly the same, which is to look at the bottom ranked relevant item. And so when we're comparing worst case preference across these pseudo populations, we're going to be looking at the lowest ranked relevant item. Now, this has connections to these Rawlsian notions of fairness or worst case fairness. It also has connections to robustness. And so here's the equivalent to Lexi Precision's preference. And the problem here is that the position of the last ranked relevant item is going to be tied for most systems. If we assume that anything that's not retrieved is way at the bottom, then this is the floor effect I was talking about earlier. So any standard recall metric is not going to be able to distinguish these systems if they're looking at the recall up to the last ranked relevant item. Fortunately, we can bring lexicographic evaluation to the rescue and do the same sort of procedure that we did before. So again, here, the bottom ranked relevant item is tied, and I can basically just go up the ranked list until I find a difference. And then in this case, I say that A is better than B because the fourth ranked relevant item is higher in A than in B. Now, this has really nice properties because its lexicographic minimum is used extensively in these extensions of Rawlsian fairness in the social choice literature. Again, we have these sorts of tables throughout all these metrics, which is demonstrating the higher statistical sensitivity of these preference metrics compared to standard metrics, and especially recall metrics, which are, in my opinion, haven't been super well developed in the IR community. So on the right-hand side, I have these plots again where I'm removing labels and I'm observing the number of ties as I'm removing labels. Sorry, this plot's a little bit different because as I'm going to the right in this plot, I'm actually degrading the number of labels. And so I'm observing that metrics like recall at 1,000 or R precision are observing many more ties as I'm removing those labels. Whereas Lexi recall is relatively stable and you're not observing these ties. All right, so let me just wrap up here. Preference-based evaluation is really nice, or I found it very nice because you're able to sort of directly compute these preferences offline without having to run any sort of human rater experiment or any sort of interleaving experiment. It's much higher in terms of sensitivity, which means then that I can evaluate systems much more efficiently. Now, there's from an IR sort of like metrics geeks point of view, there's a really nice connection between this best and worst case and precision and recall orientation that I've explored in one of these papers. And we have this explicit model of different subpopulations that even though I've looked at recall levels here, we can imagine generalizing to other types of subpopulations. There's a few extensions that I think are quite interesting. So one is, of course, going beyond ranked lists because in recommender system contexts, we're oftentimes dealing with grid orientations. Secondly, and this is something that's been on my mind recently, is that I've been talking about rankings this whole time, and rankings are great if you're thinking about information retrieval, but can I come up with an offline preference-based sequence evaluation? It's unclear. Like I think there's certain properties of ranked list evaluations I'm taking advantage of here, but if we can do offline preference-based sequence evaluation, I think this would give us a lot of power in not only evaluating these systems, but possibly optimizing them, which is the last point. So far, I've only talked about evaluation. My friends who are evaluating and building models, or who are training and building models, don't like me because I'm coming up with all these new metrics that you can't differentiate, but at the same time, they're metrics that we believe are more reliable. Okay, so at that, let me just close and I can take questions. Thank you. No questions? Yes. Yeah, so I mean, if we think about this, is the question was, are there properties of, which properties of rank lists may not apply in sequences when I'm doing these preferences? So the discount factor that we look at when we do rank list evaluation is essentially a model of where different populations of users might stop. When I do sequence evaluation, say take a Rouge or a BERT score, like what are the different subpopulations of users that are implicit in those metrics that I can tease apart? It's not obvious to me what the subpopulations are. They may be there, they probably are there, but I think we need to do a little bit more thinking about what they are. That make sense? Yeah. Yes?
So you showed these graphs that had percentages of labels after removed, but no numbers. So how many labels do you need for this?
Oh, right. So these are just fractions. Yeah, that's a good question. So I'm trying to do the math in my head. Like for these Trek collections, you have what, on the order hundreds?
Some of them have a lot, that's right.
Yeah,
So
yeah.
how does this work if you have a small number?
Yeah, so if we look at 10%, like even you're looking
No,
at,
I don't want percent. So you
no, 10% of hundreds is going to be like tens, right?
Well, but so you referenced Ellen's paper from
Yeah.
last year,
Mhm.
right? And so the main point of that paper was we have these enormous collections and we can't tell the difference between systems anymore because we don't have very much label data and there's all this unjudged stuff. So that's what I'm asking about. Is this going to be effective? You said this is more sensitive. So is it going to be able to tell the difference between systems on large collections with small amounts of label data?
Yeah, I mean, I think what's happened, so in Ellen's paper, they were looking at so the saturation of the metrics there was happening because everything was getting relevant documents at the top, right? So you had these systems that were, these deep learning systems that were just basically saturating the metrics at one, right? And so, for example, Lexi Precision would be able to deal with that because
It just ignores.
it'll go down until it finds a tie.
So then your answer would be you need enough labels to get past the ties on the easy documents, essentially.
That would be a great answer.
Okay.
Yeah.
You're welcome.
Yeah.
I don't remember the name of your metric, but the way I see the two is you do the alignment. Yeah, this one. This is remind me of a rank transfer t-test. So how do you? So what's the relation here, and what you do differently?
Yeah. So I think it's clear if you look at Lexi Precision, which remember is, what they're saying here, is reciprocal rank, right? So Lexi Precision is equivalent to reciprocal rank using the sign test if there's no ties.
No, I'm thinking about rank transfer t-test. Basically, when you do the alignment, you get the difference in ranking. So essentially, you get a list of the delta, right? If you say that each pair you compute a delta in terms of the ranking.
Yeah.
In the ranking. So you basically get a list of scores for all the pairs. Each pair has score. You have a list of the pairwise differences, and then you can directly use this score. You can straightforward just use the statistical significance test, just t-test.
Yeah.
That can tell you which system is better, what is the p-value is. So I guess what do you do differently from that?
Yeah. So I'm not familiar. Is there actual work on using rank lists, using the pair t-test with rank lists like that?
Right.
Okay. A, I want to follow up and find that work. And B, my understanding in your description is you're still looking at the magnitude of the difference, right?
Right.
Yeah.
Essentially, t-test is really try to compare the expectation of A and B. But what I think that if I actually ask my answer for my question, so what you did is when you do the expectation, you have weights in terms of that. Yeah, that's a piece of I, and p sub pi, and p of the probability of the user go down the ranked list. I is the position. So that's the probability. In that one, I don't think the t-test has this kind of.
Well, it's also if you're looking at the magnitude of the difference here, I'm passing it through a sine function, right? So I'm only looking at the preference. So it's not quite the t-test.
But yeah, yours is not t-test. But what I'm mentioning is that instead of the sign, why don't you get the sign? I just take the absolute difference. The difference f prime.
Well,
And the difference, and I replace the sign here. But I think the t-test they just don't have this t side.
yeah.
So I think in your method, in my understanding, if I understand correctly,
Yeah.
you have the weighted error
Yeah.
when you compute
Yeah.
the expectation.
Yeah. I mean, you're understanding it correctly. I think the reason why you don't want to take away the sine function is, remember, these are rankings, right? And you don't have very many relevant items. So as you go further down in the ranking, the difference is going to get a lot bigger because you're not sort of like crowded out at the top.
I'm not arguing
Yeah.
your design choice, but I'm trying to relate
Yeah.
your design choice to more well-known for decades.
Yeah. That's on me. I want to talk to you afterwards and find out more. Okay.
I feel like I maybe missed a detail, but there's nothing about this that seems like it needs to, the discussion of the formalisms, it seems like they need to be about text, except for the application domains that we're discussing, like the lexicographic website, like our text, but you also open with image generation.
Yeah.
And so I'm curious if the reason that we're talking about text is because something about the feature space is well behaved or whatever else that allows us to do this, it's easier to experiment in that domain, or if it's like fundamentally like some of these things get harder if I move to, like, let's say image ranking or other things like this.
So this is mostly about ranking. I mean, so
Right.
yeah.
It doesn't seem like it should, but the experiments seem like
They're all ranking experiments because we have these sort of, in this case, well-defined subpopulations based on recall level. It could be that you could have these subpopulations for image preferences, or like we were saying earlier, for text pairs of text strings. I don't know what that looks like. It probably does exist, but and it'll take whatever 6 months or a year for us to figure out what it is. But once you do, I think you'll have this really nice way to do offline preferences.
Okay.
Yeah.
There's nothing fundamentally. I didn't know whether or not there was something about maybe the domain that makes text comparisons cleaner, and so it's easier to get this kind of data to then do these analyses, or if there was like.
Definitely for rankings. Like, I mean, for rankings, this is the experiments were pretty straightforward to run. I mean, that's not heavy duty. Yeah. Any other questions?
All right. Well, you're in luck because he's here forever. So thank you, Fernando.
Thank you.